Let's practice applying a thermodynamic analysis to the different steps of the Carnot cycle. And so in this example problem, what we're going to do is we're going to take 1 mole of an ideal gas, and we're told that the constant volume heat capacity of the gas is 21.7 joules per mole Kelvin. And we're going to take this ideal gas and we're going to have it undergo a Carnot cycle, where the temperature of the hot reservoir is 500 degrees Celsius and the temperature of the cold reservoir is 300 degrees Celsius. Now, throughout this cycle, the gas is going to be repeatedly expanded and contracted. And so in this problem statement, it tells us the initial volume of the gas at the beginning of each of the 4 different steps. Okay? All right, and so based on this problem statement, I want you to pause the video here and kind of draw out a schematic describing this situation. And so based on the problem statement text, we could draw out a schematic that looks like this, okay? And so for this problem, what it asks us to do, it asks us to calculate the work and the heat that are required for each step of the Carnot cycle. And then at the end, we also want to calculate what the overall efficiency of the process is. So efficiency is just, the work that you get out divided by the heat that you put in, okay? All right, and so for this Carnot cycle, our hot reservoir heats the gas, and the temperature of the hot reservoir is 500 degrees C. The gas expands, and then when it contracts, the gas deposits a heat to the cold reservoir, and that cold reservoir is at 300 degrees Celsius. Okay. We're also told the initial volume of the gas at the beginning of each of the expansion or contraction steps. We're also told the constant volume heat capacity of the gas. And since we're dealing with an ideal gas, and we know the constant volume heat capacity, that means we could also get the constant pressure heat capacity. Because for an ideal gas, Cp is just Cv plus R. Right? And so we know Cp is going to be 30 joules per mole Kelvin. And that's going to be useful for later on. Okay. The other thing, just to write it out, is that the overall efficiency of the process is going to be the total work needed by the process, or the negative of it, divided by that QH. Okay. So we're going to use that sort of equation to calculate efficiency. Now for the Carnot cycle, we want to analyze each step of the Carnot cycle, so it's going to be useful to draw out, or at least write what each of those steps are. So the first step of a Carnot cycle, it's a isothermal expansion. From V1 to V2, and during this step, work 1 is exerted. In the second step, it is an adiabatic expansion. From volume 2 to volume 3, and a work 2 is exerted. In the third step, the gas is going to be compressed isothermally. So isothermal compression from some volume 3 to volume 4, and work 3 is going to be received by the gas from the surroundings. And then the final step, it's going to be an adiabatic compression. Got some dead pixels here. Compression. From volume 4 back to the first volume. Right? And this compression, work will also be received by the gas from the surroundings. Okay. All right, so this is just writing out what each of the different steps are. But another way, of course, to visualize the cycle is by drawing a process flow diagram. Right, so the gas has 4 different states, and there's also 4 different steps that the gas experiences. right? And so this initial state, the gas is going to be at TH, P1, V1. And during step 1, the gas receives QH, gives off work 1, and as such the pressure and the volume change. In step 2, the gas is adiabatically expanded, so it gives off a work 2, right? And the gas then changes to TC, P3, V3. Step 3, the gas loses heat, okay, and work goes into the system. Mechanical work goes into the system to compress it, and this causes the pressure and the volume to change. But this is done isothermally, so the temperature remains the same. But then in step 4, the gas is once again compressed, so it's going to receive work from the surroundings, and this compression is done adiabatically, so it changes the temperature back to TH, and also the pressure and volume back to P1 and V1 respectively. Okay, and so these are the different ways that we could visualize the Carnot cycle. Now this problem, wants us to calculate the work and the heat that are required for each step of the Carnot cycle. And so a good way to organize all our data is by setting up a table. So I'm going to set up a table where the first column is just going to be each of the different steps. Of the cycle. The second column, I'm going to put those initial volumes at the beginning of each step. So from the problem statement, we had 1, 1.7, 0.778, 0.457. So these are given in the problem statement. Alright, and so throughout our analysis, what we want to calculate are the work that are required for each step, the heat that are required for each step, and also, just for completion's sake, we could also look at the change in entropy of the system as well. Okay, and so what we're going to do is as we go through each step of the cycle and calculate the work and heat and change in entropy, we're going to write them back into this table. Okay. All right, and so we're essentially, to analyze this cycle, we're going to do energy and entropy balances. But there are a couple of things in our analysis that are going to apply to all the steps. Okay. And so in our analysis, if we talk about assumptions, once again, we're not going to care about changes in kinetic or potential energy. The gas that we're dealing with, we're going to assume it's an ideal gas. And also, each of the steps in this cycle, we're going to assume that they're reversible, right? No entropy is going to be generated, and the system's essentially going to be at equilibrium at all times. Another thing that applies to all the steps in our system is the material balance. Right, so accumulation is equal to input minus output plus generation minus consumption. We don't got a reaction going on, and also we're dealing with a closed system. So our accumulation will be equal to 0, and that means that the initial amount of gas in the system is going to be equal to that final amount. Okay, so N initial and final, which we'll just call N, and the problem statement told us we were dealing with 1 mole of gas. Okay, so all of these things are going to apply to every step of our process. But now let's look at the individual steps. All right, let's begin with step 1 of the cycle. So step 1 is an isothermal expansion where the temperature is just TH the entire time. Okay. All right, from our energy balance, so we're dealing with we just care about the initial and final conditions of the gas after this first step. We're going to use the difference form of the energy balance. Okay. All right. Don't care about changes in kinetic and potential energy. And also du, because we're dealing with an isothermal system, the temperature is not going to change, and for an ideal gas, the internal energy is only a function of temperature. So that means du is going to be 0 as well. So what we're left with is that 0 is equal to dq plus dw. If we integrate this out and rearrange, what we get is that q1, or qh, I should say, is going to be equal to the negative of work 1. Okay? All right, and so work, to calculate that, we could just apply our fundamental definition. So F system dx 1x2. All right. The force exerted by the gas is going to be pressure gas times the cross-sectional area of the piston. That cross-sectional area is constant, so we could put it inside the differential, multiply by x, and that gives us a volume. Okay, and we know, since this is reversible, P gas, we could say that it can be described by the ideal gas law, and so we could replace P gas with the ideal gas law. dV. We know for this expansion, it's isothermal. This temperature here is TH. And so we could actually go out and just integrate. And what we get is nRTH, natural log of V2 over V1. Okay? All right, so this is the same result we've seen multiple times in this class. Okay? All right, in that case, we know all these values. And so all we have to do is plug in. And when we plug in, we get that the work is equal to negative 3.41 e to the 3 joules. And from our energy balance, we know that QH is just equal to negative W1. So QH is just going to be 3.41 e to the 3 joules. So let's take these values and we'll put them up in our table. Okay, so we have work and Q. We got those from the energy balance. Now to get the change in entropy, we just look at our entropy balance. We'll use the difference form again. dq t plus ds gen. This is reversible. We're not generating any entropy. That goes to 0. And so what we're left with is dqh divided by th. Right? And we could plug in from our energy balance nRTH divided by th dv over v nR dv over v. If we integrate that out, what we get is that the change in entropy in step 1 is equal to nR natural log volume 2 over volume 1. This is a same result that we have seen before as well. So if we plug in here, we get that the change in entropy is 4.4 joules per Kelvin. So we could also fill our table with that. Alright, and so I went into detail about the isothermal expansion. But, this analysis that we did for the isothermal expansion is something that we've done, many times in this course already. Okay? And for all the steps of the Carnot cycle, we've done piston cylinder problems that follow either isothermal expansions or adiabatic expansions or the reverse compression steps as well. Okay? And so, for this Carnot cycle, we could actually, rather than even just starting from the energy balance or the entropy balance, we could even just skip ahead and apply the work and heat equations that we know apply to these different steps. And so now that we've done the analysis for this first step, let's move on to doing the analysis for the second step. All right. And so for the second step of the Carnot cycle, it's an adiabatic expansion where the temperature changes from TH to TC. Okay? All right, and so it's adiabatic, so we know the heat here is going to be 0, and vicariously, the change in entropy is also going to be 0. Okay? And for work, we know from the adiabatic compression and expansion problems that we've done previously that the work for an adiabatic expansion is just the difference between the final and the initial temperature divided by gamma minus 1, where that gamma is the ratio of the constant pressure heat capacity over the constant volume heat capacity. And if we take the values that we calculated at the beginning of this problem, that ratio is 1.4. Okay? So we know all these values, so all we have to do is plug in, and we get that W2 is equal to negative 522.9 joules. Okay? So we have our Q, or delta S, and our work. Let's go deposit those off. 0 here, 0 here, negative 522.9 here. Alright, that was step 2. Very straightforward. Step 3 is an isothermal compression. At T is equal to Tc. Okay? And so, the analysis for this step is essentially the same as the analysis we did for the first step. So we could just skip ahead to the end. So we know that the work is going to be nR times the temperature. In this case, our temperature is Tc. And our volumes, we start out at volume 3 and we go to volume 4. Alright, so our natural log is going to be V4 over V3. If we plug in all the values, we get 2.53 e to the 3 joules. Our work is going to be our heat is going to be the negative of the work, negative 2.53 e to the 3 joules, and our change in entropy, essentially just Q3 divided by Tc, but to write it out fully, it's this. And so we end up with a positive value for the change in entropy. So we have all our values. We'll deposit them off. And 4.4 here. Okay? Alright. And so our entropies, we have everything listed in the table. And so now we have our last step, which is that adiabatic compression. Where the temperature goes from Tc back to the original Th. Once again, Q4, it's adiabatic, it's 0, so delta S4 is also 0. work for. Once again, going to use the adiabatic work equation. Where now we're looking at the difference between TH minus TC. The work we got here is 5.26 e to the 2 joules. Okay? Alright, and so let's fill in the table here. Or actually, not 5.26, should be 5.22. Alright, so here, you get that. This is 0, and this is 0. Okay? Alright, and so we have all the works, all the heats, and all the delta S's for each step in our cycle. And so now what we need to do is to calculate that overall efficiency. Right? So for the overall efficiency, we need the total work for the system. So that's what we have to do is add up all those individual works. And from our table, we have all those individual works listed. So W1, 3.41 e to the 3 joules minus 522 joules plus 2.53 e to the 3 joules plus 522 joules. Okay, and you'll notice that for the adiabatic steps, the works here are equal. Right, so those essentially cancel out. So really, to calculate the total work, it's just going to come down to the difference between those isothermal expansion and compression steps. Okay, so when we add everything up, what we get is a negative 880 joules. So overall, the gas is giving work to the surroundings, so we're producing work. And so if we want to calculate our overall efficiency, it's minus total work over the heat from the hot reservoir, which was at QH. So what we get is negative 880 joules. So those will cancel, give us a positive, and that's divided by 3410 joules. And what we get here is 0.26, which is equal to 26%. So the efficiency of this entire process, we're only getting 26% efficiency. Okay. All right, and so that's how we could calculate the overall work from the system. But as we know with the Carnot cycle, we've seen previously, the Carnot cycle, the efficiency is just this very simple equation. Okay. So if we plug into this very simple equation here, what we get is the same exact answer. Okay. Alright, and the reason for that is because in our analysis we assumed everything was operating reversibly, right? And so that's why all these works and all these heats, add up to give us an efficiency of 26%, which is the same assumptions that are used in deriving this Carnot efficiency equation.